All right. Thank you all for coming. My name is Leyna. I'll be talking about some recent work that I've done. Not quite as glamorous as the LHC, but something that I think is equally interesting. So this will be talking about some work that actually just appeared in PRL last week, as well as some ongoing work that I'll be talking about towards the end. Okay. So I'm a condensed matter theorist. And as a condensed matter theorist, really the central question that I'm interested in is trying to understand emergent phenomena that can happen in quantum many-body systems. So quantum mechanics is a theory that we all know and love and does an extremely good job of describing the world around us. And while we understand pretty well what a single particle of quantum mechanics gives us, we understand things like wave-particle duality and the Heisenberg uncertainty principle, it turns out that when you put a macroscopic number of particles together and let them interact, this can give rise to a lot of emergent and novel phenomena that we would not expect from single particle quantum mechanics. This includes things like superconductivity, where electrons are able to conduct electricity with exactly zero resistance. Now, in trying to catalog the sorts of emergent phenomena that we see in these many-body systems, it's useful to think about these in terms of new phases of matter. So expanding upon the standard notions of solids, liquids, and gases, and including phases such as superconductors, which are intrinsically quantum in nature. So as a physicist, I'm interested in a lot of different phases of matter. Just to give some names, we have superconductors, quantum Hall phases, quantum spin liquids, topologically ordered phases. In this talk, I won't be going into detail about any one particular phase, but I want to ask the more broad question of, given some quantum many-body system, how do we perform numerical simulations of these systems? These are oftentimes extremely challenging systems to study, and numerical simulations are frequently really essential for obtaining quantitative predictions of these systems. Now, unfortunately, simulating quantum systems is extremely hard. This is something that I came to learn very early on in one of my first projects as a graduate student. We were interested in some model of interacting electrons. The exact details of the model aren't super relevant. But what is important is that we spent 6 months really throwing the weight of all the computational resources at the Flatiron Institute at this problem. Okay? And after all this work, what we had to show for ourselves is a simulation of 18 electrons. Okay? So to be fair, this is an especially challenging system. This is a model where all electrons are interacting with every other electron. But 18 is about the order of magnitude that you can expect for a lot of the interesting systems that we're interested in. Okay? And this is really in stark contrast to simulations of classical systems. So what we see here is a simulation of the classical Ising model. This is a statistical mechanical model of spins which can point either up or down, gray or red. These spins want to align with their nearest neighbors, and this energetic tendency to order competes with the thermal tendency to disorder, and that competition is what you see here. This is a simulation of over 10,000 spins that I did on my laptop in about 5 minutes. Okay? So how was I able to do this? Well, in classical statistical mechanics, the central object is the classical partition function, right? Which corresponds to a sum over configurations with a weight proportional to the exponential of the negative energy over Boltzmann's constant times the temperature. Okay? Now, you can interpret this as a probability distribution over configurations. And it's this probabilistic interpretation that really lets us simulate these large-scale systems. What this means is that rather than summing over every possible configuration, of which there are more than there are atoms in the visible universe, we can instead just sample configurations randomly according to this probability distribution. This is a problem that can be accomplished numerically using Monte Carlo methods extremely efficiently. So we never have to deal with this exponentially large amount of configurations. We can just randomly sample and measure observables to extremely high accuracy. This is in stark contrast to quantum systems. In quantum systems, we also have a partition function. This can also be decomposed, not quite into a sum over configurations, but rather a sum over world lines. so possible trajectories of each particle through time. However, in contrast to the classical case, these configurations, these world lines, oftentimes come with complex weights. They're no longer these real positive numbers that give us this probabilistic interpretation. Okay? So these Monte Carlo methods are no longer applicable, and instead we have to tackle this matrix directly, which is oftentimes exponentially large in our system size. Okay? However, this isn't always the case. There are very special models, which we call sign problem-free models, where this quantum partition function does give us a decomposition into probabilities. And these are models that we call sign problem-free models. These are very special models that we're able to simulate extremely efficiently and to extremely large system sizes. So this is sort of the rough picture I want you to have in your head. What we see here is the landscape of all quantum phases, the landscape of all possible Hamiltonians and systems we could want to study. And within that landscape, there are these very special little sign problem-free islands, these special little corners of parameter space where we're able to perform extremely accurate and large-scale simulations. Okay? So people have spent many decades searching for these sign problem-free islands. But despite all this effort, there remain certain corners of parameter space where no known sign problem-free realizations exist. Right? Certain phases of matter where no sign problem-free realization exists. Now, this begs the question, can a phase of matter have an intrinsic sign problem? Can there be something about a phase of matter that prevents it from being realized in some sort of efficient classical simulation? This is a question that people have tried to answer for the past decade. I want to briefly summarize how people have thought about it in the past, and then propose some counterexamples to how people have thought about it. Okay? So how can a phase of matter have an intrinsic sign problem? Well, how can a phase of matter be sign problem-free in the first place? So let's go back to this quantum partition function. It's now the trace of a matrix, the thermal density matrix of our system. Now, the easiest way for a model to be sign problem-free is just to demand that this matrix inside the trace is completely positive. It's made up of completely positive entries. This is what's known as demanding that your Hamiltonian be stochastic, which I think is a very silly name. ChatGPT says that Eddie Farhi came up with this, so I shouldn't be too mean. But I also don't know if that's true. OK, great. Anyways, so this is the standard method for constructing sign problem-free models. Now, it is a fact of linear algebra that if I have a stochastic Hamiltonian, then the ground state of that Hamiltonian must be completely positive. It must be a superposition of states, all with positive entries. And it's this fact that has led people to propose intrinsic sign problems in phases of matter. The logic goes a little something like this. If there's some phase of matter that has some intrinsic sign structure in the ground state and can't be made positive, that means that that phase of matter can never be realized in a stochastic Hamiltonian. And then the final step of logic that I want to take some issue with that is that if it can't be realized in a stochastic Hamiltonian, then we're out of luck. Then there's no hope for coming up with a sign problem-free model. Okay? So this is how people have thought about it for the past decade. And people have had a lot of success in proving this intrinsic sign structure in a class of phases of matter known as topological phases of matter. Now, I won't go into too much detail about topological phases of matter, but the general idea that you should have in mind is just like there are topological invariants, like the amount of holes in a surface, that are invariant under small deformations of the surface. Topological phases of matter have a lot of rigid structure to them that are invariant under deformations and are fixed properties of the phase of matter. So this lets one prove that some of these topological phases have this intrinsic sign structure as a rigid property of them. So this sign structure was first proven for the double semyon topological order in 2016. And then subsequent papers went on to prove this sign structure in pretty much all topological orders. This is a quote from last year, which shows that out of the 405 different topological orders they studied, 398 of them all have an intrinsic sign problem. So things are looking pretty grim, right, if we want to be simulating these topological orders. And this double semyon model in particular has always been kind of the poster child of the sign problem. That's always the example that you see given in talks about it. Right? So that was the status as of last year. And that makes this text message all the more surprising that I sent another Pappalardo fellow, Patrick Ledwith, last year. In this text, I express confusion and disbelief that I appear to have found a sign problem-free realization of the double semyon topological order. Okay? And I thought that couldn't possibly be true, but in fact it is. The double semyon model is sign problem-free. You can go out, you can do the simulation. This is a simulation I did showing a phase transition between the double semyon model and a trivial phase, which I did on 400 sites, I believe, on my laptop in 5 minutes. And again, this entire region right here was previously thought to be fundamentally inaccessible. But it turns out you can access it just fine. Even more surprisingly, this is simulated with completely conventional methods, right? So what I did here wasn't come up with some crazy counterexample or some new method, but I just used standard Monte Carlo methods that people have used in the past and found out that really the sign problem is just an illusion. It never existed in the first place. Okay? This is very surprising. So what's really going on here? Okay? So let's go back to this world line picture. So we decompose our partition function as a sum of world lines, each with some potentially complex weight associated with this. Now, this complex weight can be decomposed as a product over contributions at each time slice. And what this previous notion of stochasticity does is that it ensures that at each time slice, each individual term is always positive. And of course, that ensures that the overall weight at the end of the day is also positive, but this is too stringent of a condition. You can imagine a situation where locally there's some non-trivial sign structure, but globally all these signs always cancel out at the end of the day, yielding a sign problem-free formulation. And this is exactly the phenomena going on here, right? So people would look at the double semyon model, they would see this sign structure, they would say, well, we're not going to be able to simulate this, there's a sign problem. But it turns out if you just trust the process and run the simulation anyways, the signs cancel out. It's really quite striking. So this is one example. Can we generalize this to more examples? And it turns out you can. And the secret to understanding this generalization is to construct a general theory of sign problem preserving transformations. So I can imagine starting with some simple stochastic model that's obviously sign problem free. And I can imagine deforming it in such a way that preserves the global sign structure. Okay? I can take this, I can deform it a little bit more, and understanding what these deformations do for you turns out to be extremely fruitful. In particular, these deformations can be very violent and can take you between different phases of matter, which gives you access to phases of matter that you previously thought were inaccessible. In particular, this gives us access to a class of topological phases known as twisted quantum doubles. These are non-stochastic phases of matter that people previously thought had an intrinsic sign problem, but in actuality, they can be related to stochastic models known as untwisted quantum doubles via these sign problem-free preserving transformations. So there's sort of this hidden connection right here that makes the left-hand side accessible when people previously thought that it was fundamentally inaccessible. Okay. So that's all very exciting, but where does this leave us in terms of what are the true limits to simulatability and what really is the accessible landscape of quantum phases? So going back to the statistic I referenced before, out of all the topological phases, it seemed like 98% of them had a sign problem. What I've done is shown that a small section are actually sign problem free, right? So the double semyon model is the most famous one, but in the grand scheme of things, twisted quantum doubles don't actually take up that many, that much in the landscape of phases of matter. Okay? But what I think is most important about this observation is it calls into question this previous classification down here. I can no longer confidently say that all of these phases of matter down here that people thought were sign problematic are in fact sign problematic. So in work that I'm currently developing, I'm trying to understand what are actually the true limits to simulatability. Right? So people previously thought that we needed a Hamiltonian to be stochastic. What I claim is that we don't need our Hamiltonian to be stochastic, but we need it to be stochasticizable. And I did come up with that word, so that I do have myself to blame for that, right? So even if it isn't stochastic, it has to be able to be made stochastic via these sign problem preserving transformations, okay? So then this begs the question, are there obstacles to stochasticizability? That is the word that I rehearsed beforehand, because I will get tongue-tied if I don't rehearse. Okay? And what I've found so far is that chiral phases are an obstruction to stochasticizability. So there are a certain class of topological phases known as chiral topological phases. These are phases that possess some sort of circulating current of energy around the boundaries of their sample. Okay? These chiral models are known to have an obstacle to realization in a stochastic model. And it turns out these also have an obstacle for stochasticizability. Okay? So these are safe from my counterexamples. But the question of how this revises the landscape more broadly and what other phases of matter can and can't be accessible through this new understanding is a really exciting open question and something that I'm currently working on. Okay. So that is all I have to say physics-wise. I want to really thank Neil and Jane for their incredible support. I first came to MIT 12 years ago as an undergraduate. And actually, I was looking at my calendar, and I realized that it was almost exactly 9 years ago, just one day off, that I was in this very room giving my JLab final presentation. Yeah. And now I'm here, which is crazy. So it's really a blessing to be up here, to be able to thank all the professors that have helped me get here today, and also to thank Neil and Jane for this incredible opportunity to come back here and do research. So thank you to Neil and Jane. I'll be happy to answer any questions.
Okay, Will.
What does it say about quantum simulability of these systems?
Well, it means that you can. Sorry, can you elaborate what you mean by quantum simulatability?
Simulation on a quantum device.
Yeah, I mean, it says that you don't need to do it, right? Right, like I think this, yeah, I didn't touch on this, but this sort of gets at a fundamental question of like quantum advantage and what you can and can't do, or what you need to do on a quantum computer. I think this really revises the notion of where that boundary lies.
Wonderful talk. I know it's a bit besides the point, but I am curious what the double simuon problem is in the first place.
Mm-hmm.
And the other questions on the chiral models, can you also ground us there? Is there something like a fractional quantum Hall state that I can imagine having
Mm-hmm.
this property? Third question, if you have the time, what about fermions? Are they hard?
Yes. OK, let's see. So first question, what about the double semion model? So the double semion model is very similar to a more conventional model of topological order known as the toric code. So this is kind of the really basic and most simple model of topological order. And what the double semion model is it's really that with a twist, right? So it's that, but you add in some additional phases and minus signs. And it's these phases and minus signs that people thought broke the ability to simulate it. But it turns out there's some hidden connection to the simpler model. Okay? Going back to chiral phases, so yeah, you can think about these fractional topological states as one example of them. This is kind of a more broad example of states that have some non-zero chirality to them and breaking time reversal symmetry and all that. And then in terms of fermions, so this is specialized to bosonic systems. Fermions, generically speaking, are much more challenging. There's this sort of natural minus sign that always comes from the anti-commutation. You really have to deploy an entire different set of tools for numerically studying fermionic systems. And understanding exactly how intrinsic sign problems come up in fermionic systems is even more challenging. There haven't been too much work on them, because I think there are so many different methods for simulating fermionic systems, and all of them have their own different criteria for whether or not there's a sign problem. Whereas for bosonic systems, there aren't really as much. So you can talk about things more broadly.
In the back, can you use the microphone, please? Just come up here at the back of the, yeah, right, the microphone right there. Yeah, thanks.
I just wanted to quickly ask, you had a phase diagram as a function of j.
Yeah.
So you were able to prove that this entire axis is sign problem free in your definition?
Yeah, I mean, I did the simulation and there was no sign.
Right, so is that a general thing, or is that just for this specific deformation axis?
So there are multiple deformations you can do. It's not completely robust. That's always generically the case, right? For any sign problem-free model, you can always generically introduce a sign. But it's not fine-tuned to one point in parameter space or even to one axis. There are multiple perturbations you can do.
Okay.
Yeah, among these all kind of topology order, there's another one in the middle, which is with a gappable boundary. Whether those one can be fixed by your method to make them sign problem free. That's a really big class.
That's a great question. And in fact, my hypothesis is that having a gappable boundary is both a necessary and sufficient condition for being able to simulate them on a classical computer. I can't prove whether that's the case, but that is currently my hunch, that there's a connection to gappable boundaries. Yeah.
Ed?
As I understand it, your sign-free condition is something about the system in the Hamiltonian. But could you imagine sampling sign-free trajectories, so therefore just the subspace, the space space, and can you find a measure which allows you to relate that to the quantity you want to calculate?
That's a great question. So I mean, so basically you're proposing that we restrict our sampling to configurations that only have a positive weight. Yeah, so I think for a system like that, you can construct a Hamiltonian for which that is the true, that gives you the true answer for. But generally, that will be a different Hamiltonian. So it's like, you get a different answer, but you know that that answer corresponds to some other system that you can write down explicitly.
Yeah, so the question is whether you calculate the measure and whether it's possible to do that, in fact, not only for these special systems, but for general.
I think more generally it would be challenging. I think in general having, even if there is a sign, if you have some very intimate knowledge of how that sign structure occurs, you're able to go in and correct it. And there have been some examples of that in the literature.
You said that this stochasticity thing implied a criterion on the ground state, which is that its expansion in some basis has mimics of pi. That's not a basis independent statement, right?
No, it's not a basis independent statement, which is sort of the tricky thing for proving it, right? So the proof in these topological phases is that no local basis exists such that there is, such that the ground state is fully positive.
Any other questions? Okay, let's thank Leyna again.